Okay, so hey guys, today is the day 10 of our Leetcode daily until I get a job. So there's a change in the plan is that we will not do linked list next. We will do trees, graphs and backtracking and DP first. Then we will shift to the smaller or we can say easier topics because these topics are much more important than stack and queues and linked list. So we will do with the trees today and we will try to do these first 6 questions because they are all easy. So let's start with the questions without wasting any time. So this first question is subtree of another tree. So given the root of binary trees, root and subroot, return true if there is a subtree of root with the same structure at node values of subroot and false otherwise. So we have to check this if this subroot exists in a similar pattern in the same exact way in the subroot like 4 1 2, 4 as the root, 1 2 as the left and right child. Is this subtree is available in this root tree? We have to check this. Okay, so we'll just start simply. Our concept is that uh, we will try to check that. Firstly, we will try to check if these both are the same. We will use recursion obviously in while matching any of the two trees in any of the question which involve matching two trees is always done by recursion because recursion handles all the cases. We just have to handle this tree for smaller cases. For larger cases, recursion will do its job. It will generalize the things. Okay, so what we can do here is we can check this example that we are here and in subroot we are here 4 and 3. Okay, so what we can do is that uh, we can check for this root that is that left subtree equals to consist of this subroot. So basically what we meant to say is that return is subtree what roots left, and we will check. Okay, subroot and is subtree this, and we'll just do this, or it is present on the right of this root. Okay, leave it. So yeah, is subtree root right and subroot. Okay, subroot. So we will check this thing first. This is, let's say this is the step 1 of doing this. Okay, so okay, but there can be one more case, like when we go to this subroot, when we go to root of left and subroot, we will go to 4 and this is the subroot. Now we will see that these both are the same tree. We get the 4. So now we have to check if current root is equal to subroot. We have to check, right? So if we have to check through a helper function. Now at every step we will check if root and subroot are a thing. If they are, we will just return true. Okay, and if they are not, then we will go further, and then we can basically do this. Okay, in else case we can do this, and at last if we didn't find anything we can just return false. Now we have to write this solve function, that what we are doing here. Okay, up to now it's all clear, right? That if root and subroot are equal, we will just return true. Else we will check for roots left subroot and roots or root right subroot. Any of the cases return true, it's all true. Okay, so now let's check for this solve function, which is taking input as these two things. Okay, so what we can do in this is that let's just take it simple, a and b. Okay, what we can do here is firstly we will check that if both the trees are empty. If both the trees are empty, we will just return true. Okay, but if any of the tree is empty, if this is empty or if this is empty, then we will return false. that one of the tray is for empty and another is something. Okay, now if A's value is not equal to B's value, current value, then we will just return false, obviously. And then we will solve the same trees for A's left should be equal to B's left, and solve the same for right subtree of A and right subtree of B, right? And they both must be true, then only the A and B can be true, right? So recursion does its jobs. So let's say when we are here for and this, so we will send them into this function. So A and B comes here, they both are empty, no, one of them is empty, no. So A's value is not equal to B value, but they are equal, 4 and 4 are equal. So we'll just go again here. Then we will solve for force left 1 and this force left 1. Then it will come here, check if they both are empty, no they are not. A's value equal to B value, not equal to, no they are equal. So it will go further. A is left, B is left, they both are null, so it will return true. It will return true for 2 also, because the 2 has no left and right child. Same for this also. So it will overall return true, and if it's true, then it will return true that it consists of it. So I'll just try to run this. So recursion is a must, like if we are doing the, okay, yeah, if you're doing the trees thing, trees topic, binary trees or binary search tree, recursion is a must to have, because it just makes the things too easy. We just have to run the question for, wait a second, what happened here? The subtree true roots left and subroot, I guess it's right. Member access within null pointer of type tree node. Okay, we need to stop it somewhere, right? If the root is null, because we are going to left and right of root in this function only, if the root is just null, return false. Okay, yeah, so a stopping condition is must. Let me just pick up the phone, guys. Yeah, okay, so it's a busy day, so we will need to finish all them fast. So yeah, this question is done. So let's move to the next question, that is the same tree. We just have to check if it's the same tree and it's similar to this. It's similar to this function, right? And we can basically just copy this and paste it here and rename them as A and B, right? And yeah, so it must do the thing. Yeah, it did. Let's submit this. Yeah, it's good. Let's go to the next question. Balance binary tree. Given a binary tree, determine if it's a height balance. Height balance means uh, and for any two subtree, left and right subtree, the maximum difference between them must never be greater than 1. The difference between the left subtree and height of left subtree and height of right subtree can never be greater than 1. If it is, it's not a high balance. We will return false in that case. Otherwise, we have to return true here. Okay, so is the recording working fine? Yeah, I guess. Okay, okay, yeah, okay. So we'll do this. So we have to based on the height. Okay, so we can do one thing. We just firstly write a function for height. Okay, so it will be int height of a tree, that is tree node star a. Let's see, if not of a, it will return 0, and if not if, we'll just return just a minute. So yeah, let's do this. For the height, we have to just return 1 plus max of height of a is left, and height of is right. Okay, so this will return as the height. Obviously, it's a basic thing that what is the maximum height of if it's left or right, and we'll just add 1 to it for the current root node, and it will give us the height for this tree A, whichever we are passing into it. So if the root is null, then we will just return true, right? It's balanced, there's nothing in the tree. And if we will check if is balance roots right, is the right side of the root balance. But let's just check it for initially for the root only. That for the root, what we need to do is that if um, the difference of left height and right height for this root is greater than 1, then we have to return false, right? So if the absolute difference of what height of roots left and minus roots right, if it is greater than 1, we will just return false, else return true, right? And we have to check this for the roots left and roots right, right? So we'll check it here. If is balanced root left, uh, we have to check it for false, obviously. For the true, it will come here only. So if it's not balanced, we will return false, and we will just copy this thing and paste it, and we'll check for the right, right. And so let's check it. Simple, that on the right side we need to find the height for the right or left. For any root, we need to find the height for the left subtree, for the right subtree. Its left subtree height is 1, right is 2, so their difference is not greater than 1, so it will return true. Okay, but we need to check this. If let's say this is a bigger tree, right, we have to check this for all the smaller subtrees even. Okay, like for this subtree it is balanced 4 4, both sides are equal. For this subtree, when 2 is the root, it's fine that left height is 2 and right height is 1, still fine. But for 1 it is not true, right? For 1 what happens is left subtree's height is 3, right is 1, so it's not balanced, so it will return a false. So we'll submit it. Yeah, so it's done. So we'll go to the diameter of the binary tree now. So diameter is basically, what is diameter is the maximum path length between any of the two nodes in the tree, right? So like in this tree, what is the maximum length we can travel from one node to another node? Obviously that length will be between two root nodes, right? So we will start from 4 or 5 and then go up to 3. So 4 to 1 3 or 5 to 1 3, this 4 is the greatest length, and minus 1 because we are not counting the nodes, we are counting the edges only. Okay, so 1 2 and 3, 3 is the answer for this. So this way we calculate the diameter. So let's say here what we can do is that or what concept we can apply here is that we can calculate the diameter of left subtree, right, and we can calculate the diameter of right subtree, right? You understanding it? We will calculate the diameter for left subtree, and we can calculate the diameter for right subtree. And after that what we can do is that we can what we will return is that the diameter of this plus the diameter of this. No. See, what we have to do here is, let's say we will firstly go to the smallest subtree possible. Like we will go to 4, there is nothing on the left or right, and nothing on the left or right of 5 also, so we'll go to 2. So for 2 we will calculate the diameter of left, and we will calculate the diameter of right, correct? And what we will return is, what we will need for 1 is that what is the maximum diameter of out of its left and right subtree. Let's say the left subtree has a diameter of 3 and this has a 4. We will return this side, right? So we will return max of left diameter or right diameter plus 1 for this 2, 1 for this edge from 1 to 2, right? So 1 plus max of left diameter or max of right diameter, max of right left or right diameter. And at any moment we will also maintain a variable which is initially int minimum, and whenever we have this, that int minimum variable is less than L plus R, means left diameter plus right diameter. So when we are at 1, there is nothing up here. So for answer for 1 will be left diameter plus the right diameter. Like In the same way, the answer for 2 is left diameter plus right diameter. So maybe it could happen that the maximum answer doesn't include 1 or 3. It can be on the 2 only. So let's say there are a lot of nodes there or for 5 or for 4, and the maximum length answer only includes this subtree. It doesn't include 1 or this right subtree of 1. So it could be here also. So we have to compare the answer with the our current answer at all the times. Okay, so you will understand this. Let's maintain a variable firstly, which will be updating int min, and we will just find the uh, diameter for this root, and we will pass out a also because we answer also because we will check it out at every instance, and we will just return the answer. Okay, so it will be a int and we will reference this a because this a needs to be saved every time, so we will just reference it by value. Okay, so after this what we can do is, if the root is null, this condition is almost have in every tree question, we will just return 0. Okay, now we will try to find the left diameter, and that will be find diameter for roots left, and we'll provide a, and we will do the same thing for the right diameter, and that will be this. And at this moment we will compare that answer is equal to max of, okay, is here, so you can just put this answer is equal to max of answer or L plus R, LD plus RD. Okay, that will be our answer, and we have to, what we have to return is the diameter for that particular tree, and that will be 1 plus max of LD comma RD. Right, you need to understand this thing here is that our answer may be existing here, or maybe it include 1 or 3, so we have to take both the possibilities. So this function basically returns the diameter for a root. If our root is 1, it will just return the diameter for 1. It, what is that? That left tree's diameter plus right tree's diameter and plus 1 for itself, right? It will, the function will return this, but in between we will compare, in between we will compare that what our answer can be. Maybe we can find the answer in this subtree only, right? Maybe we can find the answer in this subtree, so that's why we are taking this condition here. It will include all the cases basically. So let's just try to run this. Okay, there should be answer, not a, I got, just got this answer and this. Okay, let's go to the next question. Until then, so maximum depth of the binary tree, so it's basically finding the height itself and nothing else. Yeah, it's done. So 1 null 2, 1 null 2, so it basically height plus 1, right? It's height only. So can we do it with the help of height, or we have to look for something else? um, let's just try it with the heights function. I think it should work. Return 0, else return 1 plus max depth of roots left or max depth of root, right? Okay, I guess it should work. Yeah, it worked basically. It's a simple question. So next is the invert the binary tree. So we have to just uh, make a mirror image of our current binary tree. So we have to do what is 4 4. We will make for any node, its left child must become its right child and its right must become its left child. So we just have to do this. Okay, and we just have to swap them, right? Yeah. Okay. Our video is how much time? 26 minutes. So let's try to do this within 4 minutes. So we have to do this. We have to invert the tree. So let's uh, let's try to write a function here. Let's how can we write the function is that we will go to the leftmost tree or the rightmost tree because we have to start from the bottom itself. So like we will go to first two and we will swap these 3 and 1. Now we will go to 7. We will swap 6 and 9, and then we will swap 7 and 2 for 4. Okay, so if we write a helper function for root, and so we'll just return root. We will change the existing tree only. So we will do what is void helper tree node star root. Okay, so what we can do here is that if the root is null, if the root is null, just return from here, and then we will uh, call the function for helper, call the function for roots left, then we will call the function for roots right, and after going to all the extreme cases we will just swap the left and right child of the current node. That is we can use this method, that temp is equal to a is equal to b is equal to temp. Okay, so temp is equal to roots left, root left is equal to root right, and root right is equal to 10. Yeah, I guess star. This is a this method will work for swapping, right? So you go to 4 will enter here, then for 4 we will go to left, 2 2 will go to left, 1 1 has nothing in there, so it वापस 2 पे आएगा, 2 then it will go to 3 3 is nothing there, तो वापस 2 पे आएगा. So for 2 it will swap 1 and 3. So 3 will come this side, 1 will come this side. Then it will go to again 4 and we'll go to right subtree of it. Then again the method will be uh, repeated for the same. Yeah, I guess today we did these 6 questions within 30 minutes. These were really easy questions and I could have done it earlier also, but I was just trying to explain I am doing this. So yeah, these are the 6 questions we did, and we'll try to do focus on the important things first, because in the interviews nowadays mostly DP graph and trees like these kind of questions are asked. So we'll try to focus on them first, and then we can try to improve our knowledge of every topic. Okay, so for now it's fine. So our video is for exact 30 minutes. Okay, we'll try to stop it as exact 30 minutes. So it's currently 29 minutes and 44 seconds. So yeah, from tomorrow we will try to do the 4 medium questions. Okay, if possible 5, even if it takes more than 30 minutes. So that's all. Bye.